topic by topic. And what we're going to have a look today is at the changes of state. We know that things matter consists in a state of either solid, liquid or gas, and what we're going to do is have a look at an experiment that gives us an idea about how this changes. We're going to look at the states of matter. So let's remind ourselves about these different states of matter and the names we call these by. We start off then with here a gas. We can have a liquid, and let's have a solid. And what we're going to do is we're going to change a solid to a liquid. This is in fact what we're going to do in this experiment, and that is going to be looking at our melting. We can of course change a liquid back to the solid. We call that freezing, and we can also see that one as well. A liquid can be turned into a gas, and that's either going to happen at its boiling point or just by evaporation. We can take a gas back down to a liquid, and then we can take a solid to a gas, and this is sublimation. Such as iodine, that would turn from direct from a solid to a gas, and deposition, where we get our gas straight to our solid. So this is our state of play. We know that a solid will turn to a liquid at its melting point. And this is what we're going to try and explore here as we go from one to the other. So we want a reasonable setup here to try and get this working, and what I want is a simple setup to try and get this going. Let's have a look at what we can have here. So I've got a setup with a Bunsen burner and tripod doors. I've got my beaker, and in here I'm going to put a chemical, and the chemical I'm going to put in is stearic acid. And what I'm going to do is just we're going to put a kettle on just to make some water hot to sort of start this going, which is going to quicken the process up. Stearic acid, if I bring it up to show you, is just sort of like a powder. It's almost like powdered candle, if I have to try and describe it. And what I'm going to do with this is I'm just gonna, it's not hot, it's not on, I'm just going to put some of this in here. There we are, that gives us a reasonable amount. Stearic acid has sort of another danger, which is basically it catches fire, and I'm going to put that in some water. Right, let's put the stearic acid away, put it safe. Now I'm going to put some hot water in here, and that's going to help this melt. What we're going to do then is I've got a thermometer. This is a digital thermometer, and I can place this inside my stearic acid to see what's going to happen, and we're going to send this information to, this is going to be my data capture, and what I'm going to do here is we're going to have a look at what happens. So I'm going to take readings here. I've got them set to happen every 2 hertz, that's every half second, and we got the temperature in Celsius, time in seconds, and what we should see is this heating up. And we can do this and see what happens. So I'm going to heat this thing up and we'll watch what goes on. Right, so our water is nearly hot, and we've also got our Bunsen burner, and I've got my lighter ready to go. I'm going to set my Bunsen burner so that its hole is closed, and because we're going to play around with some potentially dangerous stuff, I'm going to put my safety specs on. It's not very dangerous, this, but it's always a good idea. Right, okay, so let's start this off and see what's going on. The recording going on. And we can see that at the moment it's at nearly 26, 25.4 to be precise. And let's start this going by putting some water in here and see what happens. Now I'm using hot water here simply because it's going to sort of speed the process up, and we can see hopefully something going to start to happen as we gradually heat up this, and we'll see that this is going to start to melt. And there we are, it's starting to climb. I'm going to move this out the way, and it's going up. We're going to help this along a bit by lighting the Bunsen burner. So it is going up quite so let's start heating up the water. So Paul, if you could turn the gas tap on for me. Well, that wasn't very good, was it? Well, I got a different Bunsen burner out, and I appear to have got a rather grotty one out, so let's switch that off. And there seems to be a problem with that one, so I'll get a different Bunsen burner. We can see that it's right. Okay, I'm back with a different Bunsen burner, which I'll just plug in. Close the air hole. Let's better. That's more what I wanted to see. And we can get our heating going on. It's going to gradually go up. We're heating here, sort of going up nicely. Looking at our substance here, it still looks fairly solid. Looking at the graph, it's still going up slowly. We've got to about 60 centigrade. It's still going up nicely. And what we're starting to see now is a little bit of melting just starting to happen here. It's just starting to melt. Looking at the graph, temperature is still going up. Still gradually. We're at about 63.2. Doesn't seem to be going up very much though at the moment. Seems to be sort of hovering around about this temperature. And gradually we're seeing some melting taking place. I can see now quite a bit of liquid in here as this is all disappearing. We're largely insulated here from a lot of this stuff. This water is starting to boil. I'm not too worried about that really. Just make that safe for a moment. I don't have to heat this up too much, but we have got some liquid, you can see, and the solid is starting to melt around the thermometer. Touch it, and it's still staying around the same sort of temperature. It's taking a while to try and heat up. And now it seems to be largely skyrocketing as the temperature rises. And now our thermometer is clear of any solid, and we've just got it in the liquid. And the reason I put so much solid in there, because it does get a lot smaller in sort of basic volume when we go to from the solid to the liquid. And the water's still here boiling. That liquid is now, it's nearly all liquid. Virtually everything there has now gone. We've just got this tiny bit remaining as it sort of melts. But our temperature is still... So we're getting a change of state going along. And my experience of this experiment is that there is a sort of a classic picture of what this should look like, and this doesn't normally quite look the same. So this is our heating of the stearic acid, and I can see there it's just about all gone. and our temperature is sort of steadily going up now, and it's now at about 95. What I can't easily do is now keep heating this up much above that, because the water's only going to be at... And I've finished with the Bunsen burner, so let's turn that off. So we've heated this stearic acid up, and it has changed from a solid to a liquid. And if we look at what pictures we're supposed to get as opposed to what we did get, we get a slightly different shot. So let's stop this one and see what happened. Okay, so the temperature went up sharply, and then it slowed right down, and then it rose again sharply. When we see graphs of this drawn in a book, then they typically look like this. But from my usual experience, when we're looking at one of these, then they usually go up sharply, slow down, and then they go back up. And this is a much more gradual change. And the reason that we've got a much more gradual change is largely the amount that we're using and how much we can sort of measure. If we looked at individual atoms, it's kind of probably going to be more like this. So this here is temperature on this side and time at the bottom. So this is, if you like, the theory, what we expect with a few molecules, and this seems to be more what we get in practice, where we've got much larger amounts. And then in reality this has slowed right down here, because I can only heat my water up to 100, because otherwise it's going to undergo the same process. Now while we're doing this, then it's possible to do a slightly different experiment, which is to look at the changing of state, this time with its freezing point. I've got my liquid like that, and what I would need to do to allow this to cool down is to keep it hot like this, where it's at a constant temperature, and then put this into something like a test tube rack, and then we can see what happens. So if I get out a test tube rack, we can set this going. And this is now going to start to cool. And if I set my recorder going, this will now gradually start to cool. And in fact we can see the change better with this than we can normally see it with perhaps the heating. But again, this is going to take quite a while to cool down, and this experiment typically takes quite a long time. So it's just going to stay as a liquid for a very long time, and then gradually change to a solid. What would I expect to see here? I would expect on a cooling curve to see this falling fairly rapidly and then staying at a constant temperature, and before it starts to fall again. So here, this is a typical cooling curve with temperature against time. So what's happening? Let's see if we can have a look and see if we can look at what's going on. Well, on the heating, this point here should be the melting point. And my problem is, my melting point, when I looked at it, was very vague to have a look at. And that's largely due to the amount of substance that I had. If I had a smaller amount of substance, then this is more accurate. And that's what we do with a melting point machine. When we use this to have a look at something, we put a very small amount in a capillary tube. Very small amount, because the smaller the amount we can get, the more accurately we can do it. So we can find this, we can try and work out if we did my stearic acid again. I could have done this experiment without the water, and without the water then we could actually have found its boiling point as well. Temperature's changing. What do we call this? We call this latent heat. And I suppose what we better do is explain what that is to try and clear things up a little bit. So, latent heat. What is latent heat? So this is, if you like, the energy required to change state. If I look at a molecule, here I have my molecule, this is a solid, and as we start to heat the solid up, it starts to move faster, and it starts to vibrate more and more and more, until we reach a point where that one has there that the bond actually broke, and we're getting all of these bonds starting to break. And as these bonds start to break, so our substance will change from a solid to a liquid. So it's the amount of energy required to change these bonds, to actually break these bonds, and so that molecules then can sort of move all over one another. This isn't enough energy to turn it into a gas, but simply enough to turn it from a solid to a liquid. So we've said it's the energy required to change state. It's the energy required to change state to, if you like, to break these solid bonds. So instead we get our liquid bonds, and basically that means that we haven't really got any bonds, but these substances don't have enough energy to escape altogether. They just move around. We could do another couple of experiments, and these take quite a long time. We can have a look at what we've got here. We can change water, and my experience of doing this experiment is about as good as the stearic acid one. What I'm going to take water in the form of ice. So we take a beaker and we fill this with blocks of ice. Now our problem with filling it with blocks of ice is they're not terribly even, and what we then need to do is stick a thermometer in there. We supply a source of heat, and as we supply a source of heat, the ice is going to change to water. We then carry on heating, and eventually the water starts to turn to steam. What we don't do is to prove that we can actually do the next thing, which I find causes students an awful lot of problems, is that we can then heat the steam, and we can get the steam even hotter than 100. So if I look at a graph of this change of experiment, we start heating up, and our ice then turns to water, no temperature change. We then heat it up until it reaches its boiling point, and it stays there, and then we could heat that steam and it gets even hotter. And we find for water, pure water, this works at a melting point of 0 centigrade, 0 Celsius I suppose, and 100 Celsius. And there's a very nice experiment done by the Royal Institute, which was, could they actually manage to light a match with water? And I would certainly recommend this video to go and watch. It's quite entertaining, especially as it goes wrong several times. I know how that feels when I'm doing bits and pieces, and I know things should work, and they don't when I go live to try and stream the stuff. So let's have a look and see how you might basically light a match. To light a match, what we do is we take a container of water, basically we heat this, and this becomes steam, and so we can take a little tube out of here, and typically we'd coil this so we can get enough heat, but we'd also then heat here, and that's going to send the steam out. And this, if we recorded it, might be at something like about 300 centigrade, and that is hot enough that if you put a match, it will catch fire. Have a look for the Royal Institute trying to do this. Proves how much more difficult it is in practice than in theory. So the latent heat we're looking at. The latent heat is basically the energy transferred to a substance to melt or boil it. It's the, if you like, hidden by the substance, because the temperature doesn't change, it's the state that's being changed. The energy is used to change from a solid to a liquid, or from a liquid to a gas. We sometimes use the word fusion rather than melting. Different substances, if you like, can be joined or fused together when they melt. Evaporation from a liquid happens at its surface when the liquid is below the boiling point. However, at its boiling point, we can see the liquid boils because bubbles, vapour, form inside the liquid, and they rise to the surface. And they rise because where is the source of heat. Well, we've been leaving this experiment going for a little while. Let's have a look at how it's doing. We've got a change in the curve. We've got the curve went down from 90 to 80 to 70 quite well, and then it sort of stopped. It slowed right down. And if we have a look at how our experiment's going, we're seeing that this is now changing from a liquid to a solid. This is looking fairly solid to me. It's not quite white, it's still some liquid in there, but we are changing colour. So this seems to be a slightly better way of determining our freezing point. And our freezing point and our melting point should be exactly the same. The only problem is this does take an awful long time to go, and we can see that our temperature is falling slowly at the moment down to 63.1, 63.0, and then getting down to 62.8, well 9, then 8. So it is going fairly slowly, and it's taken it, as you can see, 12.5 minutes to get there so far. So we've got here this idea of changing of state, that energy is being used up to change state. When we're heating something, we're putting in heat, and we expect the substance to get hotter and hotter and hotter, and it's not. When we're cooling down, that energy that the molecules had moving around is now being lost, and they're turning to a solid. So we've got all this extra energy, and so although things are cooling down at the same rate, because we've got this extra energy being put in, instead of the curve going at one angle, it's going at a lesser angle. So there we have this going. So that's the changes of state to work out what's going on. Now, what do we call this? Well, this is called internal energy. Let's have a look at internal energy for a moment. Basically, substances have internal energy, still going, still losing its internal energy there. It's still looking fairly solid. Right, so let's give something a name, and we're going to call it internal energy. Now, internal energy, basically molecules have got energy, they're moving around. At the moment it's a liquid, and so we've got energy of movement, and I will call that kinetic energy. The molecules have individually got kinetic energy. They can move around. They're a liquid. But they've also got some potential energy. This is to do with their individual positions relative to one another. So my internal energy consists of this one plus that one. So this is what my molecules got, internal energy. Internal energy does not, however, include gravitational potential energy or the kinetic energy of me moving something around. So my rubber here has got internal energy. It's got energy of its molecules relative to one another. But if I move it or I drop it, we are looking at that as extra energy. This has got energy all by itself, internal energy. Basically, heating a substance is going to change this internal energy. So, if it's changing its energy here, it's changing it because we've got more or less PE. We've got more or less KE. Heating, it's basically going to increase this energy, but it will probably lower some of that before it will increase the potential energy. When the temperature of a substance is increased, then we need to worry about something else called the specific heat capacity. I've looked at that in an earlier video, where the change in energy here equals the mass times something called the specific heat capacity times the change in temperature. We often refer to temperature as this symbol theta. When the physical state of a substance changes, the total potential energy of its particles will also change. We've got here our latent heat, the energy required to change its state from one to another. And if we've got latent heat, then we could actually measure this, and our latent heat is our change of energy, I suppose, here again is going to equal the mass times this thing called the latent heat of fusion. Now, that we can measure by heating up perhaps something like ice, which is what we'll have a go at next time. What's the difference then between a solid, a liquid and a gas? And we're looking at this thing here, internal energy. So, in a solid, what have we got? Well, we've got strong forces of attraction. Each particle, we know, can vibrate about its point. And we saw this with this model, where the atoms are fixed, but they are vibrating about a point. So we're going to say it vibrates about around an average point in space, an average position. So when a solid's heated, the particles' energy stores here increase, and they vibrate more and more and more until the bonds break and it becomes a liquid. So what do we know about the liquid? Well, we've still got our strong forces of attraction, and they are still holding the molecules sort of together. And I suppose it's going to be either atoms or molecules together. But these are weaker than a solid. Basically, we can move away, but we can't move away enough. So our kinetic energy here is increasing until we reach a gas. And then there are basically no strong forces trying to hold them together. There's no real forces at all holding these atoms or these molecules together. They move at high speed. They move in all directions. And in fact, something that is not necessarily obvious is that when we heat a gas, again we can add Ke. And as we do that, we find that something does change. We can see that the pressure is then increasing. And we can do that in another experiment. So let's see if we can summarize what we've done so far. We are cooling my substance. It's still going. It's gradually here changing temperature, and it's not falling very much. It's only got now down to about 50 centigrade. So this line much slower, and whereas the book would do this as a straight line which is horizontal, I've got my line going down slowly, and we can see it's just looking like a solid there, but obviously it's still liquid, a bit liquid inside, because it's changing its sort of form from a liquid to a solid. So what can we determine from all of this that we've actually done? Well, we can say simply that for a pure substance, its melting point is the temperature at which it melts, which is also the temperature at which it solidifies. Its boiling point is the point where it boils, where it changes from a liquid to a gas, and that is the same temperature at which it will condense. And we require energy here to change it from a solid to a liquid, and a liquid to a gas. Boiling occurs throughout the liquid when something's boiling, whereas evaporation only takes place at the surface. So there are some differences there. When we come on to internal energy, we can say that increasing the temperature of a substance is going to increase both its kinetic energy and its potential energy, so it's going to increase its internal energy. The strength of the forces attracting between two particles, or even more particles, explains really why it's a solid, or it's a liquid, or it's a gas. A high amount of forces makes it solid, lesser it's going to be a liquid, and virtually none means it's going to be a gas. When we try and heat up a substance, the temperature rises, the kinetic energy of this rises. As it starts to melt or boil, the potential of the molecule changes, the potential energy, because the molecules are now further apart. And as we heat up a gas, the pressure of a gas is the amount of movement of those molecules as they hit the walls of something. So we see pressure in something like a balloon, that it's still sort of stiff because the molecules are bombarding at that system, pushing it away, giving it quite a lot of potential energy. So next time we're going to have a look at a similar experiment where we're going to take some ice and we're going to heat that. This experiment is still going on. We're seeing the temperature still gradually fall. It's still going after here 27 minutes. It's still falling at a very constant rate as we're trying to change the solid, the liquid, into this solid. When it gets there, then this graph will look again quite steep. So we've got a steep bit, a shallow bit, and then it should go steep again. So I hope you've followed that. I hope that made some sense. If you liked what you saw, then please subscribe, and I will see you next time when we'll have a look at specific latent heat on this physics GCSE topic by topic. Thanks for watching. Stay safe. Goodbye.